Okay, I will indeed be doing some lecturing. In fact, the homework that's due tomorrow requires what I'm going to talk about today for the most part. But before I start doing some lecturing, I want to point out this right here. I spoke with Corinne yesterday. She now has a date for when we have to have the project poster stuff turned in for the printer. And so Friday, April 13 at 3 p.m. is when Dr. Corinne McNeil, needs the PDF document for your poster. And you have the examples out here of previous year's posters to give you, insights and the resources that are in the lab guide, well, the links. It's important to let you know about the date so that you don't forget it. Yeah.
There is, I know you spoke briefly about a template for
yeah.
poster. Where is that again?
It should be on Moodle. Let's go look, because when I say it should be, it's not quite as convincing as if I said it is.
Yeah.
That course. It should be up here near the top. There. That sample poster. That's the template. Okay. We will not do that. All right, where we left off yesterday, we had this clicker question. Now, you don't have to get out the clickers. I don't have this operating, so it's not going to be important to answer the quicker questions. But we ended with this question: what happens to a transverse wave when it is transmitted from a slower to a faster speed string? And so the frequency cannot change. That's part of wave physics, that the frequency cannot change. So if the frequency can't change and the speed changes, then the wavelength is going to change the same as the speed does. So the wavelength will get longer when it goes into something faster, shorter when it goes into something slower. See, were there any others? Yep, that was the only answer on this slide. The next one, the question we didn't get to: what happens to a transverse wave when it's reflected from a string with a faster wave? When there's a reflection, that's when you have a new thing to consider. Now, when it's reflected, is the frequency going to change? No. Is the wave speed changing if it's reflected? I'm looking at Ed because he's the only one that's answering me. He says no again. No. So if the wave speed stays the same, the frequency stays the same, what does that say about the wavelength? It's going to stay the same. So we're going to have no changes in wavelength. We're going to have no changes in frequency. Then we have the phase idea. The answer I'll give you now, and then we'll go to the next slide and review what we learned before. There's no change in phase either. Hence, there is no change when it's reflected from a string with a faster wave speed. So how do the reflections work? This is really important for understanding the thin film process. When you have the wave reflecting off a boundary that has a slower speed, that's like having a wave on a rope that goes from a lighter rope to a heavier rope. The heavier rope has more inertia. Because it has more inertia, it's resisting the change in motion, and it tugs on those string. And so it's going to cause the reflected wave to be inverted if you're going from the faster to the slower. So the reflected wave, faster to slower, is inverted. If it's the other way around, if you're going from slower to faster, the faster medium, the lighter rope, has less inertia. It's not tugging as hard as the other rope was. In that case, the reflected wave is not inverted. Now, what does inverted and not inverted have to do with what we're doing? This has a phase shift of pi radians or 180 degrees, or we sometimes will say 1/2 wavelength as well. If you're reflecting off of something with a slower speed, the reflected wave has a phase shift. So a wave that comes in like this will be reflected back inverted from that. So it makes a difference when you're looking at a thin film. You have to pay attention to which material is the faster of the two. Now, just to make sure it's 100% clear, we had the phase inversion. Was it on reflection or on transmission? On reflection, only on reflection, never on transmission. And was the phase inversion occurring if you hit a faster medium or a slower medium? A slower. So phase inversion only for reflection off of a slower medium. Final question to make sure it's all clear. What does the index refraction tell us about speed? Which one has a faster speed, a higher index or a lower index? The lower index has the faster speed. So that means that if you're reflecting off of something with a lower index of refraction, then you're going to have a phase inversion, the half wavelength pi radians phase shift. If you're reflecting off something with a higher index of refraction, no phase shift. This picture illustrates that. So now we can actually come back to this picture. Remember, we had gone through this picture. We had said that this reflected ray would be about 5% of the incident intensity, and this one would be about 4.7 something percent. It was like 4.7, let's just go back. 4.51%. So the intensities of those two are pretty similar. It's 90%. One is 90% of the other. To determine if we're going to have constructive or destructive interference, we need to look at the relative phases to see if they're in peak at the same time or if they're peaks at different times. So to do that, we first look at this reflected ray here. So the first reflected ray, it's reflecting from N1 to N film. If N1 is equal to air, then it's reflecting off of something with a slower speed. What does that tell you about the phase shift? Does it have a phase shift if you reflect off slower speed or if you reflect off higher speed? It's when it reflects off the slower speed. So we're going to have a change in, well, the phase shift for one is going to be equal to, and I'm just going to put it in radians, so pi radians. Radians are unitless, so I just put pi. So that's the phase shift for the first one. Now the second one does three things the first ray did not. It travels through the film, it travels back through the film, and it had a reflection. So I have to take those three things together. With it, when it travels through the film, is it going to have a change in phase? I'm going to say yes, it has a change in phase because it's going through, it's taking time going up and down. So I need to calculate how much that phase is going to change. So what I'm going to do is say, well, how many wavelengths did it go through? And then it's going to have 2 pi radians for every wavelength it went through. So since it goes through this twice, I'm going to have 2 times the thickness. T here is thickness. Notice T is thickness, not time. 2 times thickness is the distance it traveled. How many wavelengths is that going to be? Let's put it into practical numbers that you'll be able to get an answer. Let's say that I travel a distance of 5 miles. My wave travels a distance of 5 miles, and it has a wavelength of 1 mile. How many wavelengths did it go through? What did you say? 5. How do you come up with 5? I took that distance of 5 miles and I divided it by the distance for one wavelength of 1 mile. So we'll do the same thing here. We have a distance of 2 times the thickness. What's the wavelength in my film? If it's lambda 0 is wavelength in vacuum, the ACUUM, then what's the wavelength in the film? The wavelength in the film, we had this in class yesterday, is that wavelength over the index of refraction for the film. And so this is going to have to be divided by the wavelength in the film. That should have been an F there, not an N. That's how many wavelengths. Now to calculate the phase, how many radians do I go through in one wavelength? One wavelength is, one cycle is how many radians? 2 pi. So I'm going to take this number of wavelengths and multiply it by 2 pi to get the phase difference of going through the material. Then I have to look at the reflection. Did the reflection have a phase shift here? Let us go. This was supposed to be air, water, air was what we were doing when we started this problem. I shifted to air, glass, air later on, but air, water, air. If it's air, water, air, if it goes from water to air, does the reflection have a phase shift or not? The answer is no, because it reflected off something with a higher speed. It only went to lower speed. So that's my phase shift for the second one. There's one thing I want to change in that equation. I have the wavelength in the film. I want to put it in terms of the wavelength in vacuum. And so there I use the index of refraction of the film as indicated by this equation. So that's the change in phase for that reflected ray. So I found the change in phase for the 2 reflected rays. How do I determine if these are going to be in phase or out of phase? If they're going to have constructive interference in phase or destructive interference out of phase? What was the condition for constructive interference or for in phase? Okay, if they reach their peaks at the same point, which means that their phase difference has to be 0 or an integer multiple of 2 pi radians. So for constructive interference, I have phase difference, which is going to be phase 2 minus phase 1, is equal to an integer multiple of 2 pi radians. So I just take the 2 phases I have, 4 times the thickness times pi times n of the film over lambda 0 minus pi equals m times 2 pi. I'm going to change the color on that because it is looking like I'm all in one equation now. Now what I have here is an equation of the condition for constructive interference. So I'm going to finally solve this for thickness. So the thickness that will give me constructive interference, I'm going to have to add pi to both sides. And I will have 4 thickness pi n final over lambda 0 is equal to pi times 2m plus 1. Well, it doesn't take a genius to say let's cancel those pi's, and then solving for thickness. And these are the thicknesses that will give me constructive interference on reflection. Now notice this process is the process you'll have to know for the test. I won't be giving you an equation for constructive or destructive interference because there's actually 8 different variations that are all using the same principles. There's only 2 answers, but there's 8 variations to get those 2 answers. So this here is one of the answers. What was m in this equation? Let's go back to where it was introduced. It was introduced right there. We said to be in phase, we had to have a phase difference of an integer multiple of 2 pi. So m here was any integer. It could be positive or negative, although notice that a negative integer would give me a negative thickness, which is not physical. If m is 0, that gives me a positive thickness, so that's physical. So in this case, it's going to be 0, 1, 2, etc. So those different thicknesses will give me constructive interference. And notice that thickness depends on the wavelength. So a blue color, something with a wavelength around 400 nanometers, is going to have a different thickness for constructive interference than red that has a thickness of 700 nanometers. That's why when you look at that thin film, you see different colors, because for different thicknesses, different colors have constructive interference. Now, if we had done destructive interference, how would this calculation have been different? Well, it actually just comes to this here. We had the condition for constructive. For destructive interference, what does the phase difference have to be? What does destructive interference mean? They're out of phase. They're adding up to 0. So being out of phase means that they're going to have to be pi or 3 pi or 5 pi, which is going to be m plus 1/2 times 2 pi for the phase difference. And so I would just do the last part with that condition for destructive interference. Now, as I said, this is not the general equation. We have 2 equations that come out of this, the one for constructive and the one for destructive. It's going to turn out to be similar, but I'm not going to do it just because I don't want to get myself confused. The reason I don't give it to you is you could be going from air to oil to water. I think you have a homework problem that's air to oil to water. What's different there? You're going from faster to slowest. Why would that make a difference? well, it's the thickness, or not the thickness, but the reflections. If you're going from air to oil to water, and if you're increasing the index on each one, then that means you're going to have a phase shift on both of the reflections. If you went the other way around, you'd have no phase shift on either of the reflections. So you have to look at your situation to determine where you have phase shifts on reflection and where you don't to build your final equation. Erika.
So my question, going a little back, how did you get to T back there?
Because the light has to go through the film and then back again.
So
it travels a distance of 2 thickness.
Oh, so the other ones don't count then? Because it was.
I was only comparing rays 1 and 2.
Okay.
Now, what's the difference between rays 1 and 2 and rays 2 and 3? The phase shift between 2 and 3 will be exactly the same. But the intensity of 3 will be much, much lower. Yeah. So you need to be able to go through and derive your equation, to be able to find the equation like I did for a given situation. Now, a couple things that I didn't say, I've gone through all of that, were how to do the problem. How to do the problem. First, sketch the first 2 reflected rays. If it's transmitted, now remember the transmitted had a difference of about 90% between these two. So it's very different for the transmitted, but you could be asked what condition gives you constructive interference for transmitted and what condition gives you destructive interference for transmitted. For transmitted, the light's the same until it gets here, and then you'd have 2 reflections on that ray, one here and one here, and no reflections on this one. That's the difference. So you could have to do the transmitted as well. You want to look at what you have for the phase shifts on the reflections. So if it's on the transmitted, both of the reflections would be only affecting B, ray B. If it's on reflected, then you have 1 reflection for ray 1 and 1 reflection for ray 2. You have to identify are those phase shifts or not. Make sure you draw your diagram like this. And even though our problems are pretty much always going to say that the light comes in normal, it needs to come in pretty close to normal for the reflected ray to be on top of the first and the second reflected rays to be on top of each other. If the light's coming in at some angle like this, they're going to end up separated and not interfering. But for our work, we always draw them with a little slant so you can see the difference in the paths. So that's this first one. Even if the problem concerns normal incidence, draw the incident ray with a non-zero angle of incidence so that you separate the rays. Decide whether you have the phase shift for each reflection that's going to occur in the 2 rays that you're considering. Then find the path length difference between the 2 rays, and from that, the phase difference due to that path. And then calculate the overall phase difference with the rules for constructive interference and destructive interference. Now, I have a problem here, but since we're in lab and we need to get to lab, I'm not going to do any calculations other than to explain why the film appears black at the top. If we look at our equation for constructive interference, the minimum thickness for constructive interference is going to be, when M is 0, is going to be that thickness. If it's any thinner than that, you're going to have destructive interference. So when we look at this picture, it starts really thin and gets thicker as you go down because, of course, the water, gravity is pulling it down to make it thicker at the bottom. And so up here, it's really thin and it's all destructive. Here, you're getting thick enough to start having constructive interference on the reflected light. And so that's why it's black at the top and then becomes bright as you go through different thicknesses. The reflected, the next parts are just putting numbers into the equation. Now, double slit interference. Double slit interference is best illustrated by just doing it. So here's a laser. Let me turn off the classroom lights. Holding this in my hand is kind of hard, but I'm going to use things here to stabilize it. Also figuring out which one is two slits. I think. Yeah, holding it by hand is not the best plan. Let me try it on this. So I have the laser pointing here. Can you see that at all? Yeah. Okay, as long as Angelina can see it, we'll be good. Right? So now I'm going to adjust this so that light goes through, actually here. See this funny pattern? You have a bright spot at the center. Probably you should just come on up here, because you're not going to be able to really see it unless you're up here. So come up. Come on, come all. Okay, so see that laser? That's easy. Now when it goes through a double slit, I have different slits here, and you see different patterns depending on which slit's going through. Okay, now that I turn off the lights, it's even harder to see. Okay, there's like we had before. See how the center's really bright, and then it has alternating bright and dark spots. Bright and dark, bright and dark.
Yeah.
That's what we call a diffraction pattern. That's caused by light going through just two slits. Thomas Young showed the world that light has to behave like a wave because of this action right here. You have lots and lots of places where you have constructive interference, where you have a bright spot. This is light going just through two slits. If the light was going through two slits and it was BBs going through the slits, you'd have them basically blocked unless they go through, and then you just have a bright spot here, a bright spot here, corresponding to which slit it went through. Different slit combinations give a different pattern. Let's see if I could. Yeah, there's a different slit combination that's different width of the slits, and you see now the pattern's different. Since it's more than two spots, that says that it's got to be a wave, that you have the light waves going different distances, going through one slit versus the other, and then interfering to give you multiple places of constructive interference. If it was particles, what would you have seen? Just two spots. So you can sit down. That's actually why I want to make sure everyone saw. Because, I mean, if someone gets a Nobel Prize for that, we should at least look at it. So it showed that light behaved as a wave. After the test, we're going to learn about light behaving as a particle. But right now, we have light behaving as a wave. And so how does light behave as a wave? Well, we've seen already one example with the thin film interference. This diffraction is the second one. If the light goes through two slits, one slit here, I'm going to change the color, one slit here, and one slit here, then according to Huygens Principle, each slit is going to act like a new point source of light, and we're going to have light coming out, and this is showing wave fronts. Wave fronts, places where we're at a peak. At the places where those wave fronts cross, we're going to have constructive interference. And geometrically, it turns out that that forms lines of constant angle. So that's why we have multiple spots of constructive interference, because it's where those wave fronts intersected. Now we're going to do a little geometry to figure out where those occur. We're going to start by making sure you remember, what does it mean for light to be coherent? If it's coherent, then you have a fixed phase relationship for all of the light. So you can, if you know what the phase is here, you can know what the phase is everywhere. That fixed phase relationship is important. And with the coherent light, if they are in phase, if their peaks are the same place, then we'll have constructive interference, where the amplitude is equal to amplitude of one plus amplitude of the other. So intensity, the intensity of light is the power per unit area. Now, what is power? That was the power of a lens, which is very different from power. That was the power for the lens, so it's not an unreasonable thing to say. Energy per time. So the intensity is telling us how much energy is deposited each second per square meter. That's what the standard unit would be, the watt. So the, actually, it's the watt per meter squared, excuse me. Since the intensity is proportional to the amplitude squared, that is, the intensity is proportional to the amplitude of the electric field squared, then if I have one wave with amplitude A1, one wave with amplitude of A2, if I add those together and I have constructive interference, then the amplitudes add. And I will have an intensity but if we expand that out, we have the intensity of the first plus the intensity of the second plus this term here that is 2 times the square root of the first intensity times the second intensity. So if I take 2 waves that are in phase, one of the interesting things is the intensity I get is bigger than the sum of the 2 intensities of those waves. The energy per second per unit area is bigger than it would be if I just had one wave and then the other wave added together. That's actually kind of a surprising thing. Now, we know that we can't get something for nothing. It's not like we're creating energy, but we have a higher intensity than if we added them. And likewise, that's just the same thing. If we have destructive interference, then the amplitudes subtract. And if I do the same calculation, the intensity is the sum of the 2 intensities minus that same factor. Now, I said we can't get something for nothing. What we're going to have then, if we look at the intensity over space, if this is the intensity we had with, adding one intensity to the other intensity, it's going to sometimes be higher, sometimes lower. So the average is what we would have had just adding the intensities. But it's going to have peaks, higher intensity, valleys, lower intensity, where we had the dark spots. This is a slide to make sure we understand coherence. There's 2 questions here. Obviously, we're not using the clickers. So just blurt out, are the 2 sources coherent? Is there a fixed phase relationship between those 2 sources? Go ahead and blurt. What was that?
Because when it goes down, there's like a point where it meets.
Okay, I had to know I had some locations. It says the sources. The location where I measure isn't going to matter for the source. It's only at the source that the question was asking. Is there a fixed phase relationship between the waves coming out of those two sources? From that picture, we see that, yes, they have been following the same pattern of peaks and valleys. So they have a fixed phase relation that makes it coherent. Even if this one had been going like this, it still would have been coherent. It just would have been out of phase, but it would have had a fixed phase relationship. Because the coherence is, do they have a fixed phase relationship or not? Same figure. Is the sound at her location going to have constructive or destructive interference? It's going to be destructive because they're exactly out of phase. When one's at its peak, the other's at its minimum. Now, at the sources, they were actually in phase. So why is it destructive at her position when it's in phase at the sources? Okay, I have a lot of answers, which is great. I didn't hear them. That's not as important as you guys thinking and answering. She is a different distance from source 1 than she is from source 2. And so even though source 1 and source 2 were in phase, at her position, she's hearing them out of phase. So she's getting destructive interference even though those sources were in phase. Why is she getting destructive interference? The distance from source 2 is 3 1/4 wavelengths. From source 1, it's 2.75 wavelengths. So the phase difference here is going to be 2 pi radians per wavelength times that difference in path length, L2 minus L1, which would be 2 pi radians times 3.25 minus 2.75 is 1/2. So that's pi radians is the difference in phase. Pi radians, half a cycle. I could have also just said it's 1/2 wavelength out of phase and saved myself, but I wanted to be consistent in how I did the calculation. Save myself a little effort. So it's out of phase because the path lengths were different by 1/2 wavelength. So it's easier to say change in path length is equal to 1/2 wavelength, therefore destructive. If they had been different by 1 wavelength, it would have been constructive because they both would have been peaks at the same time again. So we can use the path length difference to determine if it's constructive or destructive interference. So in general, if the path length difference is an integer multiple of the wavelength, it's constructive interference. They're in phase. And if it's a half integer multiple of the wavelength, then it's destructive interference. They're out of phase. In both of these equations, m is just an integer, including 0. This last one, we're not going to focus on at all. If you have different media, that is like if you have the problem we did in class yesterday with the Michelson interferometer, where we had the cuvette that we took the air out of, so it was a different medium. Then you have to keep track of the number of cycles in each medium separately, like we did in class yesterday. Here's a practical example. Instead of having 2 slits, we have 2 sources. Or actually, we have 1 source and 2 reflectors. So we have a wave coming out of this source, reflecting off and coming here, going off the source, coming back to here. Those come together and they interfere. And so you're going to have some distances for the second reflector where you have constructive interference, some where you have destructive interference. Just to make life real simple, realize that to go from here to here to here and compare that to here to here to here, the difference is doing this path difference twice. So the difference in length for the 2 paths is 2 times x. Now here's data to go along with the power as a function of distance x. And you see that it had a peak here, a peak here, a peak here. Why did we have peak powers at 3 places, minimum powers other places? We have the 2 waves. I'm going to zoom out so we can see both pictures. We have the 2 waves. We're moving the second reflector out. M, by the way, stands for mirror there. And at different positions, we have stronger and weaker signals. Why? Go ahead, Aaron.
Could it be like the ones where it cancels it, so because of them going different, so like it goes down instead of being all the way up?
Right. These are destructive interference. And the ones on top were constructive, making it bigger. And so we've learned the conditions for constructive interference. Delta L is equal to M lambda. For destructive interference, it was delta L, the difference in path length, is equal to M plus 1/2 lambda. So since the change in path length is equal to an integer multiple of lambda for constructive interference, then this distance right here must be how much? I mean, we can measure the distance by looking at the numbers here. But how much in terms of wavelengths must that be? Remember, the path length is 2 times x. How much does the path length have to differ for it to go from constructive interference to constructive interference? Okay, the path length has to increase by 1 wavelength. And since our x is half of the path length change, then that means this distance here must be 1/2 of the wavelength. So that 2 times 1/2 wavelength gives me 1 wavelength. The total path difference is a wavelength. And so I can look at this and say, well, it's easiest to go out here. Here's another 1/2 wavelength. So going from about 0.3, let's say 0.39 to 6.5 is 1 wavelength. And those are units of centimeters. So we get the wavelength is approximately 2.6 centimeters. So we can determine the wavelength by looking at the positions where we got constructive interference. An example of light behaving as a wave. Now back to some other examples. We all like to listen to or watch things that are on CD or Blu-ray or DVD, and those use this phenomenon. You have a laser beam that is focused on the compact disc, and the compact disc has some plastic here, and underneath the plastic you have this thing. There's a difference in height there for the reflected light. And based on the difference in height, you have a difference in phase between the light you sent in and the light that gets reflected back. So this here is actually, this is your light source, reflects up here, comes back down, and you compare the interference between your light source and what came back to determine if it's a pit or not. And that's how the data is stored. If it's a pit, or if it's I forgot what they call the high area. So it's using this phenomenon, which is totally cool. Now, finally, the geometry that makes our diffraction grating work. coming back to, it's the same idea of being in phase or out of phase. This picture here is not realistic to what we do. What we do, we have the spacing here between these things is very, very small compared to the spacings, or excuse me, to the distance this way. But to make a picture fit on the screen, we draw it as if it's not. But we have light coming out through multiple slits, and we have different path lengths. So if I go from here to, from here to here, and here to here, those were different path lengths. If the path length difference is an integer multiple of the wavelength, it's going to be constructive. If it's a half integer multiple of the wavelength, it'll be destructive. And so we simply have to do some geometry calculations, and we can determine the angle. Now the angle, notice, is measured from the normal to the center of the slits to where the interference forms. So that's the angle theta. We just have to determine what the path length difference is a function of angle, and we'll be able to have an equation to tell us where we have constructive, destructive interference. This picture here should look familiar. That's essentially what you're seeing when we looked up at the board. So the key is, in the far field approximation, we have a small angle. This alpha is approximately equal to 0, which makes this a right angle. Both of these angles down here are right angles. This is your classic 90, 90, 0 triangle. I say your classic because nobody considers that a triangle. They consider that a straight line. But it's very close to that. Because these two sides are approximately parallel, the path length difference is just this side of a triangle. So this is the separation between slits, given the label D. This theta here, by similar triangles, is the same as the angle for us measuring where the interference maximum is. And then just using the definition of sine theta is equal to the opposite side, the path length difference, divided by the hypotenuse, d. So the path length difference is equal to d times sine theta. So that's how we calculate the path length difference. If it's constructive, what was the path length difference? Say louder. I know that somebody's answered, but I can't tell at all what's being said. This is something we've gone over about 4 times today, so everybody should have it at the tip of their tongue. Not double. We had a specific phase relationship for it to be constructive. It had to be an integer multiple of wavelengths for the path length difference. And so that means that I have delta L is equal to m lambda is equal to d sine of theta, where m is any integer. And it can be positive or negative integer, so we usually put -3, -2, -1, 0, 1, 2, like that. So that's for constructive interference. What about for destructive interference? Destructive, it has to be out of phase by a half, so m plus 1/2 wavelengths for the path difference. Whoops, my finger moved it, or my palm, I mean. So that's our equation for destructive interference. After all we've done, it's kind of anticlimactic to get to the equation for constructive and destructive interference for a double slit. Now this was just for a double slit. Our experimentation today is going to use a diffraction grating. What's the difference in a diffraction grating and a double slit? Well, these diffraction gratings have 600 lines per millimeter. 600 lines per millimeter means my beam is about 1 millimeter wide. It's going through 600 different slits. And so I have the same equation for constructive interference between any two slits, but with 600 different slits, if it's not exactly constructive, there's going to be so much phase difference that it's going to average to destructive. So for the difference between a diffraction grating and a double slit is simply that okay, so these are the equations we just worked out. For a diffraction grating, we have the constructive interference and destructive everywhere else. So if I take my same laser beam that we used here with the double slits and I put through the diffraction grating, it's going through the diffraction grating. Where's my light? There it is. My finger I'm having a hard day. Where's my light? Remember, what you never do is look through the light. Oh, that's because this is not my diffraction grating. I picked up the wrong one. Here's the diffraction grating. Okay, so I put through diffraction grating. Now, yeah, I had reflections. It's almost perfectly parallel, so I'm getting a reflection that's going from this down to the laser and reflecting back off it. That's what the second lines are. I just tip it a little, it gets rid of it. Notice those are very distinct dots. And it's dark everywhere in between because we're adding together from 600 different slits. If it's partially out of phase, it's out of phase by a different amount at each slit and thus averaging to zero. So we have very distinct dots. Those are very far apart because the separation between slits here is very small. What's the separation between slits, you ask? Glad you did, because it's something you need to know. If we have 600 lines per millimeter, then the distance between slits is 1 millimeter divided by 600. So the distance we use in that equation is the separation between slits. You just invert the lines per millimeter to get the millimeters per line for the separation. So obviously you need to use that. That's diffraction. I'm going to skip over Young's work here. What happens to the diffraction pattern? I just answered this. If the distance between the slits is decreased, what happened to the separation between the bright spots? If the slits get closer, did they get closer together or did they get farther apart? Farther apart, right. Spacing between them increases. Now you just saw it experimentally, but we could also just go back to our equation here and note that the angle, sine of the angle is m lambda over d. So as d gets smaller, then sine theta is getting bigger, which means theta is getting bigger. And so you can see from that equation that they had to get farther apart as it gets smaller. This is just going through the grading. This is kind of like what you saw when we turned on this lamp and looked through the diffraction grating glasses. I say kind of like because this is actually made by having a film on a semicircle around it instead of having the glasses on your face. If you use a light source like this, a line source, you get the discrete lines. And this is what you see from a specific gas, and I don't even remember what gas it is. But each gas will have a different set of lines. It's going to be very important in our future. We will not at all talk about the single slit, so you don't need to worry about that unless you are, in Physics 252, where we talked about array today. And so we go to our last, not our last thing. I talked about the size of a telescope's objective being important, or a microscope's objective being important. In fact, it was a microscope when we talked about specifically. We talked about the numerical aperture the bigger the numerical aperture, the more light it gathers. And it turns out that a bigger numerical aperture can be achieved by making a bigger diameter objective lens. The same is true for a telescope. A bigger diameter objective will gather more light. And telescopes, the most important thing for most telescopes is a big light gathering ability. So bigger opening is better for a telescope. But there's a second reason that also makes it better. And that is, of course, a telescope or microscope has a circular lens. We've just done geometry for parallel lines. The geometry for a circle is different. We're not going to do that calculation, but Lord Rayleigh did. And Lord Rayleigh came up with the criteria for determining when we can resolve something with a microscope or telescope. And he said that we'll be able to resolve it to tell if we have two objects or one object if the maximum for the center maximum of one is at the diffraction minimum for the other. And so it has to do with this diffraction for the resolution. And because closer spacings made wider diffraction maximum minimum, it turns out that with a circular aperture, the bigger your aperture, the bigger the opening, the smaller the spacing between your maxima and minima, and thus the smaller details you can resolve. And so a bigger opening for a telescope or microscope gives you a smaller angular resolution, which means you can resolve smaller angles, which is better. So the size of the aperture is very important. And the equation for the circle, there's your first order diffraction minimum. We're not going to have any other equation for the circle except for this one for the first order diffraction minimum. And so two things will be resolved if their angular separation is bigger than what that equation tells you. So that's Rayleigh's criterion. Here's a picture to illustrate Rayleigh's criterion. Maximum of one. Actually, this is not the minimum of the other. This is maximum and maximum, but it's actually maximum on minimum for his criterion. And, oh my goodness, I thought I had a couple more slides here. We'll shift now to the lab guide for the last bit. So lab guide, missed. We have two things that we're going to look at in lab today that deal with the wave nature of light. The second one actually is what we've just gone over, that diffraction. You're going to have your own experiment that will make multiple measurements, at least 3 measurements, to confirm that the equations that we came up with for diffraction maxima, you're going to use the diffraction grading, so only the diffraction maxima are accessible. So at least 3 measurements that confirm that. And your process, how you're going to do it, is up to you. You could use a gas source like this and measure, if you know it's helium or know it's hydrogen, and measure the angles for the diffraction or the peaks, the lines. That's one way of doing it. There's lots of options. I leave that to you. The second thing, or actually the first one here, is polarization. Now, polarization is super, super cool. I love to do my demonstrations of polarization, and I think you'll love them too because it's very cool. So for these demonstrations, once again, I'll need you to come up here so you can actually see the demonstrations. Yeah. And then we got to change the lights. Okay, so that's just a light bench. Here's a polarizer. Now what polarizers do is they work only with transverse waves. Polarization occurs because with the transverse wave, you have the displacement is perpendicular to the propagation direction. And in that case, you could have, if a wave is traveling from me to Christian, the wave could have displacement going like this, or like this, or like this, any direction that's perpendicular to the direction between me and Christian. A polarizer is going to limit the direction of the displacement to one direction. So right now, light is going from me to Christian with different polarizations. If I put this between us, it's now only allowing vertical oscillation of electric fields. And so when Christian looks at me through this, he sees less light because it's blocking the light that was not vertical. So I put this on here, and of course, you see that it's darker. On average, and this should be really good statistically, 50% of the light can be this direction and 50% this direction. If the light was in this direction, you just break it into components and say it's this much in this direction and this much in that direction. If I put a second polarizer and the polarizer is aligned with this, how much more should the second one drop the light?
Are they in line?
If they're lined up, they're the same.
They should be the same.
Okay, should be the same. That's the correct answer. I tell you it's the correct answer before I do it, so you recognize that it's not exactly the same. That's because these aren't perfect. They're absorbing some light even, when it's not following polarization. Or when it is following polarization. Now, if I rotate it, what should happen?
It should block all the light.
Okay, it should get darker until it blocks all the light. So I rotate it. You don't really notice it getting darker at first, but once you get to about 45, you can start seeing it. And sure enough, kind of cool, right?
Yeah.
What's going to happen if I keep rotating?
It's going to go back.
Okay, it can't get darker than black. It starts going light again. And so now they're parallel again. Now that was all fine and good. Here's another polarizer. So I'm going to put this on here. Is that parallel or perpendicular? Parallel. Put this one on parallel. Okay, so we have three polarizers all aligned. It's really not that exciting. Now I'm going to rotate it. What's going to happen as I rotate it? Okay, that was really not surprising, was it? Now I'm going to take the top one and rotate it by 90 degrees. So now the bottom one is allowing light this way. The top one's allowing light this way. What will happen if I rotate the one in the middle? Okay, he says to get lighter. What did you say? Okay, we have stays the same or get lighter. Of course, this is physics class. We have to do it, right? So I rotate it. Clearly, it got lighter. How the blazes does that work? We use it as an analogy for quantum mechanics. It's not quantum mechanics, but we use it as an analogy. The bottom one is only allowing light like this. The top one's only allowing light like this. And yet when we have one in between, it allows some through. The answer is the one in between was saying, well, how much of the light is aligned like this? And as I said, we can break it into components. We have light like this, and we say, well, part of that is perpendicular, and that's not going to be allowed through. But part of it's parallel, and that amount was allowed through. So the one in between changed the polarization. And then that new polarization had some that was going this way. And so it allowed some through. Now we'll see the law of Malus that relates these in a few moments. But I have more demonstrations that are beyond awesome. Those are the boring parts. If anyone wants to play with my 3D glasses, you can, but it won't be part of my lecture. Here's a piece of paper with a very cool first initial on it. R. R, which stands for, I don't know, looking around for somebody whose name besides me stands with R. Rebecca, yes. I made it just for her. Every year I use it for Rebecca. So if you look through there, Angelina, you're the closest. What do you see when you look through the calcite crystal?
2 R's.
2 R's. but there's only one. And it's not because the crystal's not perfectly cleaved. If it was perfectly cleaved, it'd just be clear that there's two R's. Obviously, this must have something to do with polarization because I grabbed my polarization. I'm doing this in the polarization lecture. Put the polarizer on top. What do you see, Angelina? Keep watching. As I rotate it, what happens?
Oh, 2 R's, 1 R.
It changes from one R to the other R.
Yeah. Yeah.
Okay, so let's shoot for some ideas of what's going on here.
It blocks certain lights, so like it doesn't looks refracted when all of light goes through. But
It looks what?
refracted.
Refracted. When the light goes from the paper into the calcite, it's refracted. And what determines how much it's going to be refracted? The index of refraction, or the speed of light. Well, since it's separated into two distinct images, we must have two distinct speeds of light for refraction. So we have two refractions. And by looking at this, we can determine what's making the difference between the two speeds of light. Different orientation for the polarized light. So we call something like this birefringent. It has two speeds of light depending on the polarization. It has the ordinary and the extraordinary axes, is what we call it. So that's really kind of cool. Okay, if you don't think it's cool, well, poo on you. I think it's totally cool. So let's go with something more. You guys have heard of things like racemic mixtures, right?
Yes.
What does it mean if it's a racemic mixture? You have what?
1 to 1.
1 to 1 of?
Chemistry.
Both have some of the like mirror images.
Okay, what do you call them?
Oh, yeah.
Something like that. Yeah.
I don't, it's been a long time since I took organics, so I don't remember exactly what it is, but I know what it is. The racemic is you have equal amounts. How do you measure that to see if it's a racemic mixture or not?
Is it with like the
Using polarizers. Using polarizers with light. So why? Because the left hand versus right hand, cause a rotation of polarization. So if you put a polarizer down, and then you put your mixture that has either a left or a right or some combination, and put another polarizer, you'll have a rotation of the polarization. And here you see it depends on the color of light. Why? Because the thickness of the film compared to the wavelength is going to determine what colors have the polarization blocked or not. So different thicknesses are going to give us different colors. So they use a specific color of light to do their measurement. So change in the orientation of the polarizers will choose different colors that have been rotated by the right amount to get through. It's kind of cool, right? That's just using cellophane tape. Well, somebody, before I arrived, because God knows I do not have the patience for this, made Union College's iconic symbol. So here we have it. A clock tower with a nice blue moon and a white sky. Sound right?
No.
Clearly, we should rotate this. And there we have a nice white moon and a black sky with the beautiful clock tower. And you know, that person you think had patience. What about this one? This is my coup de grace. I'm very patriotic. Of course, when I was a child in Liberia, I was very patriotic. The Liberian flag, in case you don't know, it's just like the United States flag, except for it has one star. It's kind of like Texas, with the, because it's only one state in our country. So, once again, that doesn't look right. I rotate it, and now there's good old flag. Now, some other things you should recognize right away. How many stripes are on the flag? 13. This has 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. Yay, it wins there. How many stars are on the flag?
50.
50. How many does this one have? 1, 2, 3, 4, 5, 6 by 1, 2, 3, 4, 5, 6, 7, 8. 48. You know what? Union College's been around for a long time. Up until 1949, we had only 48 states. So, it's just an old flag. Good to know, right? It's before I was born, okay? That's my my cool demonstrations for polarization. Now we'll talk about the law of malice and we'll get started. So go ahead, go back to your seats. Okay. The law of malice, or Malice's law, has to do with how much light gets through a polarizer. So first, some basic rules. If we have unpolarized light and we go through a polarizer, how much light gets through on average? 50%. So the intensity, change to this one. Of going from unpolarized light through a single polarizer is going to be 50%. Now, in the step we're going to use following this, you'll see something that looks a little different than that, and you'll say, wait, why didn't you use that? The reason is you have to integrate over the circle, and we're not doing calculus here. So we're just going with 50% and not integrating over the circle. Besides, it makes perfect sense for half of the light to be this direction, half of the light to be that direction. So now we're going to put a second polarizer. A second polarizer is typically called an analyzer. So if you read a problem that says the analyzer, it just means the second polarizer. And the analyzer has some angle theta between the first polarizer and the second polarizer. And so the electric field that went through the first polarizer was aligned with the first one. With the second polarizer, I want to find how much of this electric field that went through the first one is parallel to the second one. So I'm breaking into components. There's my right angle because I want parallel and perpendicular components. Which side of my triangle is the electric field that went through? Well, yeah, you had adjacent, opposite, or hypotenuse, and that's the adjacent side. What's the trig function that relates adjacent side to the hypotenuse, what E1 is? So we have cosine of theta is equal to electric field 2 over electric field 1. So that means electric field 2 is equal to electric field 1 cosine theta. Now, intensity is proportional to the electric field squared. So the intensity 2, let's write it this way. That way there's no mathematical ambiguity. Electric field 2 over electric field 1 is equal to cosine theta. If I square both sides, then I will have intensity 2 over intensity 1, because intensity 2 is proportional to electric field 2. Intensity 1 is proportional to electric field 1, so the ratios are equal, is equal to cosine squared theta, or the law of malice, intensity 2 is equal to intensity 1 cosine squared of theta. So here we have those two equations right there. The intensity transmitted is the intensity incident times cosine squared of the angle between the original polarization and the second polarizer. Now, what happens if I put a third polarizer in? A what? I think she's saying ooh. I don't know. Q.
No, like 3 times.
Oh, okay. Okay. She's probably thinking correctly. What you do is you just treat each polarizer separately. So if I have 3 polarizers, let's say I have unpolarized light. Whoops, that's not unpolarized light. So unpolarized light will draw like this with intensity I0, and then it goes through my first polarizer that's like this. And so I will have coming through that intensity 1 equals 1/2 intensity 0, 1/2 because it was unpolarized to polarized. And then I put a second polarizer at an angle theta 1. And so coming out of that, you can have intensity 2 is equal to intensity 1 cosine squared of theta 1. And then I put a third polarizer that's at some angle theta 2 from the second polarizer. Notice I'm going from the last polarizer to the next one. And I would have intensity 3 is equal to intensity 2 cosine squared theta 2. And so to get the intensity 3 in terms of intensity 1, I would just substitute theta, or intensity 2 there, substitute intensity 1 there, and I would have an equation that gives me intensity 3 in terms of intensity 0. So you just daisy chain them, if you will. Keeping in mind that each new polarizer is changing the orientation. So that's the second thing, well, the first one in the lab order, that you're going to be looking at. What do these have in common? These are two phenomena that can only occur if light is behaving as a wave. So we're looking at things and we're going to verify that two laws that say light's a wave are correct. So your hypotheses are the law of Malus and how diffraction grating works. So you should have, I saw a polarizer and it dimmed the light, and that's because, according to the law of Malus, I1 is equal to I0 cosine squared theta. And so then you're going to have your test is a test that will test to see if that's true. The classic test is to take your polarizer. So in your, see those blue boxes, those are your optics kits. You have little polarizers, and they have angles marked on them. And so you can put those polarizers one after the other. You can adjust the angles between them, and you can measure the intensity of the light that goes through. Now, I have to go to biology and steal what somebody didn't accidentally leave in my classroom. We have one of them here. Biology has a bunch of these things that allow us to move our light detectors around. Here's the light detector. Goes into the USB link, and the USB link actually goes into the computer without having to use the data studio. And so using these, you can use the Capstone software and measure the intensity of light. It has 3 different settings here. You want to use the lowest, or excuse me, the one that gives the highest numbers, but not saturated. So start with light just coming through one polarizer and adjust. You have the low light, medium light, and high light. Adjust to the lowest light setting that doesn't saturate, that doesn't give you a constant, not changing number. Make sure you have this fixed so you're looking down the axis of your polarizers, and then you just measure how much light you get through at different angles. Now you're going to find that these polarizers are a little less than ideal. Just like you saw my polarizers here, didn't give us exactly what we expect. They don't block 100% of the light that is not aligned with it. So you're going to have to take that into account. Say, did it theoretically fit but show error, or did it not fit at all? So you're going to do an experiment to confirm the law of Malus gives you a reasonable prediction. The second experiment you're going to do is going to be something, like I said at the beginning of class, where you are measuring the diffraction angles and checking to see if they match what we learned here today for diffraction gratings. So you could find the diffraction angles, make at least 3 measurements. We don't want just one measurement and say, that's good enough. we want to have consistency. But measuring the angles for instance, a hydrogen lamp or a helium lamp, look up what the wavelengths are, or determine what the wavelength is for a helium neon laser. Whatever it is that you want to do, you want to have an experiment that's going to allow you to test to see if that's true. So each experiment is a small experiment. I want you to think about how you do it yourself rather than me tell you, because as I was telling another student earlier, if you're doing research, nobody's done the research before you. You're not copying something. You're thinking about how can I make this measurement that hasn't been done before. These things have been done before, but not by you. You need to think about how you would do it. Any questions? Nope. All right. Have at it, my friends.